let us explore an intriguing question that connects biology with fundamental physics. Can quantum physics, rather than just scaling laws, explain why smaller organisms have shorter lifespans? And could this be correlated to the timescales of elementary particles and quantum processes at the sub-nanoscale? Biologists have long observed a pattern. Smaller organisms tend to live faster and die younger. Mice, for example, live only a few years, while elephants and whales can live decades or even centuries. Traditionally, this is explained using metabolic scaling laws such as Kleiber's law, which shows that metabolic rate scales with body mass to the 3/4 power. As smaller animals have faster metabolisms, burn through energy more quickly, and accumulate cellular damage at a higher rate, leading to shorter lifespans. But is metabolism the whole story? Some researchers have wondered whether quantum effects at very small scales could also play a role. For instance, at the molecular level, many essential biological processes, DNA replication, enzymatic reactions, electron transfer in mitochondria, occur on timescales close to quantum transitions. These events involve tunneling, coherence, and discrete energy changes, not just classical chemistry. You might ask, could the timescale of life processes be anchored to the timescale of quantum events? Elementary particles, such as electrons or photons, operate at incredibly short intervals, fractions of femtoseconds. Biological processes, although much slower, still rely on these subatomic transitions as the building blocks of energy conversion. It is tempting to speculate that smaller organisms, which operate with faster metabolic rhythms, might be more directly tied to quantum level rates, while larger organisms buffer these processes with slower systemic rhythms. Another way to think about it, quantum fluctuations set a physical clock at the sub-nanoscale. In a small organism with a high surface area to volume ratio, the number of these fundamental transitions per cell accumulates more rapidly relative to its total size. Over time, the higher frequency of energy turnovers could lead to faster molecular wear, more replication cycles, and accelerated aging. Larger organisms, by contrast, might have more redundancy and regulatory systems that slow down this clock. Is there evidence for this? So far, most lifespan studies still attribute differences primarily to metabolic rate, telomere shortening, and accumulated damage. But researchers are now exploring quantum biology, a field studying how quantum effects shape processes like photosynthesis, magnetoreception, and enzymatic activity. If quantum mechanics influences biochemical timing in ways we don't yet understand, it could hint at a deeper link between physics and biology. Why does this matter? Because answering it could reshape our understanding of aging and longevity. If lifespan is connected not only to metabolism, but also to quantum-level processes, we may uncover new strategies to slow down or even reset biological clocks. It could also change how we think about the relationship between life and fundamental physical laws. This question remains open, but it invites us to look beyond classical explanations and ask whether the rhythm of life might ultimately be tied to the rhythms of the quantum world. Smaller organisms tend to have shorter lifespans and faster metabolic rates than larger organisms. Traditionally, this pattern is explained by scaling laws such as Kleiber's law, which relates metabolic rate to body mass. These laws assume that energy use and cellular processes scale with size, leading to more rapid aging in smaller species. However, there are exceptions and outliers that scaling laws alone cannot explain. This raises the possibility that deeper physical principles, such as quantum effects, may influence biological timescales. A mouse lives only a few years, while an elephant can live for decades, even though both are mammals. It is like small cars wearing out faster than large trucks, because their engines run at higher RPMs. At the sub-nanoscale, quantum physics governs the behavior of elementary particles such as electrons and protons. Quantum processes occur at incredibly short timescales, often femtoseconds, 10/15s or shorter. If biological systems are influenced by quantum coherence or tunneling, their efficiency and timing could reflect quantum-level processes, the hypothesis suggests that the shorter lifespan of small organisms may be linked to faster decoherence or energy dissipation at these scales. This concept moves beyond classical energy budget models. Quantum tunneling of protons in enzyme reactions occurs much faster than classical models predict. It is like a teleportation shortcut that speeds up a journey compared to walking the entire distance. Classical scaling laws, while useful, do not explain why similar-sized organisms can have very different lifespans. They also fail to address how some small species, like certain bats or turtles, live much longer than predicted. This suggests that size and metabolism alone do not fully determine longevity. Quantum-level phenomena, such as differences in electron transport chain efficiency, might help fill this gap. Considering quantum physics could refine our understanding of aging and lifespan diversity, naked mole rats live far longer than other rodents of similar size, defying scaling law predictions. It is like two cars with the same size engines, but vastly different fuel efficiencies because of unseen design differences. Mitochondria, the energy factories of cells, rely on electron transport and proton gradients that are subject to quantum effects. Quantum coherence and tunneling can influence the speed and efficiency of these processes. If smaller organisms experience faster quantum fluctuations or decoherence, their cellular energy systems might wear out more quickly. This could lead to higher oxidative stress and damage accumulation. Such processes would link lifespan to quantum physics rather than purely to metabolic scaling. Photosynthetic complexes use quantum coherence to transfer energy with near-perfect efficiency, showing quantum effects in biology. It is like using synchronized waves to push a swing with minimal effort. But losing synchronization leads to wasted energy. Elementary particles like electrons and protons have intrinsic properties and characteristic lifetimes. Some researchers hypothesize that biological systems might be subtly synchronized with quantum fluctuations or decay rates at the subatomic level. This could set fundamental time limits on cellular processes, especially in smaller organisms with less buffering capacity. If true, lifespan could be partly constrained by universal quantum timescales. This idea remains highly speculative but intriguing. Atomic clocks rely on electron transition frequencies, suggesting that particle behavior defines precise time intervals. It is like using a cosmic metronome that ticks at a universal rhythm, influencing everything built around it. Quantum decoherence, the loss of quantum coherence due to environmental noise, may occur more rapidly in smaller organisms. Faster decoherence could disrupt delicate processes like DNA repair, electron transport, and signal transduction. This would accelerate cellular damage and aging. Larger organisms, with more complex regulatory systems, might better buffer against decoherence. Linking aging to quantum decoherence introduces a new layer of explanation for lifespan differences. Quantum coherence in bird navigation is disrupted at higher temperatures, suggesting environmental effects on quantum biology. It is like trying to maintain a whisper in a noisy room. Small systems lose coherence more quickly. Evidence for quantum effects in biology is growing but remains fragmentary. Studies on photosynthesis, avian magnetoreception, and enzyme catalysis show that quantum processes can persist in living systems. However, direct links between quantum physics and lifespan remain unproven. Testing the hypothesis would require measuring quantum coherence and decoherence rates in organisms of different sizes. Advances in quantum sensing may make such experiments possible. Nitrogen vacancy centers in diamond are being used to probe quantum effects in living cells. It is like developing a microscope capable of seeing the invisible vibrations of the quantum world. If lifespan is influenced by quantum processes, it could transform how we approach aging and disease. Interventions might target quantum-level processes, such as coherence stabilization or electron transport optimization. This perspective could also reshape evolutionary biology by explaining why some species evolved exceptional longevity. It might help predict which organisms are most resilient to environmental stress. Such a paradigm shift would unify physics and biology in a new way. Stabilizing mitochondrial quantum processes could hypothetically extend healthy lifespan in humans. It is like reinforcing the foundations of a building to prevent it from collapsing prematurely. The idea that quantum physics influences lifespan challenges our classical understanding of biology. It suggests that life's timing could be linked to the deepest layers of reality. Whether or not the hypothesis is confirmed, exploring it pushes the boundaries of interdisciplinary science. It may also illuminate why life is structured the way it is, from cells to ecosystems. Such questions remind us that biological time may be rooted in quantum time. Even if the hypothesis is not fully proven, it inspires experiments that uncover new layers of biological organization. It is like realizing that the ticking of your watch may be connected to the heartbeat of the universe.